Okay, let's see the contents first of this video. First, I will explain you the denoising scheme using the Wavelet Transform, and then I will explain the Anaconda and then Spyder for Python code development, and then I will explain the Python package, which is the SciKit-image that will be responsible for denoising images using the Wavelet Transform techniques. And from the same Python package, I will explain this denoise wavelet function that will be used for image denoising. Then I will show you the example Python code for denoising the grayscale images, and then I will show you the Python code for denoising the color images. Before going ahead, I recommend you to watch these three videos first. The first one is the introduction to the wavelet theory and its application. So if you go through this video, you will get the ideas of about the wavelet theory, that what are the wavelets, and how the wavelet transform is computed for the signals and images, and what are the different applications of the wavelet. The links are given in the description. And the second video is about the wavelet based denoising of the one-dimensional signals using Python. So that is a video about the Python based denoising of 1D. So this is just the current video is just extension of this video. Okay, here we are denoising the 2D signals, and this video is about the denoising of the 1D signals using Python. And the last one is the wavelet transform analysis of images using Python. Here you will see that how the wavelet transform is computed for the images using Python. And now let's see the some theoretical background. When a signal is transmitted over some distance, obviously it is corrupted by the noise, and the simplest noise model is this, which is defined by this equation. So your corrupted signal, which is f dash xy, is obtained by adding this noise into the original signal fxy. We have some basic assumptions for this noise nxy, that this noise is additive in the nature, and this noise is a random signal, probably the white Gaussian noise with a zero mean value, and it's of high frequency. So here our objective is to remove this noise nxy from this corrupted image f text xy using the wavelet transform technique. Okay, this is the wavelet based denoising scheme. Here you can see that first your signal fk is decomposed using the discrete wavelet transform into the various wavelet coefficients, generally the approximation coefficients and detail coefficients. And these detail coefficients are thresholded, okay, by some thresholding function, and we get the thresholded detail coefficient CD dash. The approximation coefficients remain unchanged, and then we collect all these wavelet coefficients and taking the inverse transform to get the denoised image or signal f dash k. The question is here that how to estimate the noise level and how to set these threshold values. So we have different types of methods, such as universal threshold method, which is also known as the visit shrink, the Bayes method, shear method, and minimax, etc. And using these the noise estimation functions, we set a threshold. So once the threshold is set, we threshold or we shrink all the wavelet detail coefficients like this. So we have the two ways, basically the hard and soft thresholding. In hard thresholding, we shrink the wavelet coefficients like this, that in a range minus lambda to plus lambda. If the wavelet coefficients lying in this range, then they are neglected, zeroed out, and the wavelet coefficients beyond this range are remain unchanged. And in soft thresholding, the wavelet coefficients within this range are zeroed out, of course, but the coefficients beyond this range are also degraded or shrinked by some constant value as shown here. Okay, so this is the basic scheme which works to denoise the images or signals using wavelet transform. Now let's see that where we will develop the Python code. So for the Python code development, we will use the Anaconda distribution. Anaconda is a free package manager and it is easy to install, and it offers the community support also. And worldwide, over the 19 million users, it is the industry standard for development, testing and training. You can download this Anaconda from this link. The link is given in the description. The one good thing is that Anaconda has more than 7,500 packages and libraries to support various development of applications. It supports NumPy, SciPy, Numba, Pandas, Matplotlib, TensorFlow, etc. And it includes the IDE, one IDE, which is a Spyder. And the Spyder IDE I personally like very much because its GUI is very similar to the MATLAB, as I am a MATLAB coder, so I like this Spyder very much. And for image denoising using wavelet technique, we will use one image processing library, that is a SciKit-image in Python. For more information, you can go to this link for documentation. And this is the package which is already available in the Anaconda, so there is no need to download it separately. Install it. The SciKit-image, or in short SciKit, it's a toolkit of SciPy which provides a versatile set of various image processing routines. Okay, so it's a very powerful, and under the restoration of this library, you will get the wavelet based denoising functions. The SciKit-image, it offers the two main functions for wavelet based denoising. One is the estimate sigma function and other is the denoise wavelet. So the first function is used to estimate the standard deviation of the noise from the noisy signal, and the second one is used for the denoising. Right now this library supports only the two methods for denoising. One is the Visu shrink, that is the universal threshold, and second is the base shrink. Default, as you know that MATLAB supports more functions, more methods such as shear method, min-maxi and FDR, etc. So MATLAB is rich in this case. So let's see this denoise wavelet function, how it can be used for grayscale images. So this is the general syntax for using for base shrink first. Later I will explain for the Visu shrink. So here the Y is your output. So that is your denoise output image, and X is the input, and wavelet equal to the W name. So that is here you will define the name of the wavelet used, such as har, dB, coif, bio-orthogonal, etc. And then mode equal to S or H. S or H, that means it is a thresholding mode. So either you will write soft thresholding or you will write the hard. And then wavelets equal to wavelet labels equal to n. So that means the number of the decomposition labels. So here you will write some number. For example, if you write 3, it means there will be the 3 decomposition labels of the signal X. And then denoising method, it's a base shrink. Obviously, since I'm explaining for base shrink, so you will write base shrink denoising method, and then rescale sigma. Here you will write this either true or false. Okay, so it is used if there is some internal rescaling of image, then the sigma rescaling is also done. And now denoising using Visu shrink. So that is a general syntax for Visu shrink. So X is your input, you will define the name of wavelet, and then you will define the S or H, that means soft or hard thresholding, then number of decomposition levels, and then method is obviously the Visu shrink, and the rescale sigma T or F, that means true or false. So one thing extra is there, so that is sigma equal to sigma EST. So that is not used in the base shrink method. It is used here. Why it is used here? Because For better control over thresholding, that means to avoid the over smoothing of image, in Ring, the standard deviation of noise should be found first. And you can find the standard deviation of the noise from the noisy signal using this function. So that is the estimate sigma function. You pass your noisy signal x, and you put average sigma equal to true. So once you execute this function, this function will estimate the noise standard deviation from the noisy signal, and then by controlling the value of this sigma est, which is the estimated standard deviation, you can control the over smoothing of image. So sometime you need to decrease it. For example, if let's say the estimated value is sigma, then sigma equal to sigma est, you will write either divided by 2 or divided by 3 to adjust the over smoothing. And now let us do the denoising of color images with the same function. Everything will remain same except these two more attributes will be included in the function. So one is a multi-channel which has the value either true or false, and second is the convert to YCBCR which also includes the value true or false. So what is the multi-channel? The multi-channel means if it is true, the wavelet denoising is done separately for each channel, because color images are of 3 channels, RGB or YCBCR. Okay, so for each channel the denoising will be done separately. Now what is convert to YCBCR? If it is true and multi-channel is also true, then wavelet denoising is done in the YCBCR color space instead of RGB. The default is RGB, but if you write convert to YCBCR true, then the denoising will be done in the YCBCR space instead of RGB. And it is observed that doing denoising in this YCBCR has an improved result as compared to the RGB images. So now let's see the example Python code for image denoising of the grayscale images. First you need to import some libraries. So we import matplotlib for plotting, for showing the images, and then from SciKit-image under the restoration we import the denoise wavelet and then estimate sigma, those two functions. And then from SciKit-image we import the random noise. That means we will add the noise to image to make it noisy. And then we have one matrix which will be used to calculate the PSNR between the two images. So we will calculate the PSNR between the noisy image and the denoised image to see the improvement. And then we import the SciKit-image.io that will be used here to represent the image as float. So when you execute this first command, I am using the SciKit-image.io imread to read this image that is residing in the current directory lena.bmp and representing that image as a float. Okay. Now I am deciding the sigma equal to 0.1, that is the noise standard deviation, and then I am making a noisy image which is the imgn. So by the using function random noise of SciKit-image, I am passing my original image which is the noise free and adding the noise. So this is the noise variance which is the sigma square. So imgn is my noisy image. Okay, now from this noisy image I am estimating the value of standard deviation. So by executing this estimate sigma function, this noisy image is passed and making this attribute true, I'm getting the noise estimation in the sigma est. Okay, then I call this function for denoising. So that is denoise wavelet function. First, I'm using the base method. So my output image is, which is the denoise, is represented by the img underscore base, and imgn, that is my noisy image. Method is the base shrink, because I'm getting the output using base, and the mode, thresholding mode is soft, and the wavelet decomposition level I'm using 3, and the wavelet for denoising I'm using the biorthogonal 6.8, and the rescaling of sigma is true. And in the same program I am getting the denoise output as a visu string also. So my output is stored in the img visu string, that is my denoised image, and calling this function again, denoise underscore wavelet, and imgn is my noisy image, method is visu shrink, thresholding mode is soft, and sigma, which I have estimated using the sigma est, I'm getting that value, and I'm adjusting this value to control the over smoothing. So instead of taking the full value, I am just taking the 1/3 of this value. So when you execute this program, you can see the effect of this adjustment. So I recommend you to first take the whole value, and then see that how much over smoothing is done there, and then after that you control its value to get the better results so in your code. So I recommend you to do this controlling of sigma. And then wavelet decomposition level I'm using 5, and the wavelet I'm using the biorthogonal 6.8, the same wavelet which I have used in the base method, and the rescaling sigma is true. So after executing this, I get the denoised image in img visu string. And these are the codes to get the peak signal to noise ratio, PSNR. So the first will find the PSNR between my original image, that is img, and this is the imgn, which is the noisy image. So the first line will give the PSNR between the original image and the noisy image, and the second one is calculating the PSNR between the original image and the denoise image, by which is obtained by the base method. Okay, and the third one will give the PSNR value between the original image img and the image denoise image, which is obtained by the visu shrink. And these are some plotting commands. So I'm using the subplot of matplotlib library, and here I am plotting my original image, so that is img, and the color map uses the gray. And here I am plotting my noisy image, which is imgn, and here I am plotting my denoised image, which I get from the base method. So that was img underscore base, and here I am plotting the denoised image, which I am getting from the visu shrink. Okay, and this is here I am printing all those 3 PSNR values which are obtained between the original image versus noisy image, original versus denoise using visu string, and then original versus denoise using base method. So let me execute this program in Python, and let's see what type of result I will get. So let me jump to the Spyder. So this is my Spyder IDE, and this program is already written here. To save the time, and just pressing this run button, I will get the results. Okay, so this is the result which I achieved. Let me zoom it to see. This is my original Lena image, this is the noisy image, and this is the image output which I get from the base method, and this is the output which I get from visu string. Okay, so now let's see the PSNR values. The PSNR between original versus noisy image is this 20.059, and then PSNR between the original versus denoise using VisuShrink is 28. Obviously, that is an improvement of 8 dB from 20 to 28. And then PSNR between original and the denoise using base method. So this is the 29, which is further improvement of 1 over the VisuShrink. So yes, obviously I'm getting the good result using this method. So let me jump to my presentation. Next, let me show you the Python code for color image denoising. So for color images, as I said, everything will remain same except the 2 more parameters will be included in the denoise wavelet function. So so first let me import those libraries same which we have imported in the previous example. So and here I am reading another image, that is the peppers. It's a color image, it's a RGB, it is RGB color image and representing that in the float, and then defining the noise standard deviation, that is 0.15, and then adding the noise to the original image to get this noisy image IMGN, and then estimating the sigma noise standard deviation using the estimate sigma function. Yes, this is the inclusion of the extra attributes as compared to the previous one. So since in the previous example we were denoising the grayscale images, so we did not write this multi-channel equal to true. So if I am writing multi-channel equal to true here, means that the sigma will be calculated for each RGB channel, and then we will do the average, and then we will estimate the value of the noise standard deviation here, and then executing this denoise wavelet function. So IMGN is my noisy image, method is the base shrink, thresholding is soft, decomposition level is 3, and the wavelet used here is the coeflet 5. Obviously now these are the 2 more attributes written here, that the multi-channel equal to true, that means the denoising will be done for each color channel, and then convert to YCBCR equal to true. It means instead of RGB denoising, the first image will be converted to the YCBCR space, color space. It will be denoised there, and then it will be converted back to RGB, and then rescaling of sigma is true. And now this is for denoising using VisuShrink. So here the noisy image method is VisuShrink, thresholding is the soft thresholding, and again I have adjusted the value of the estimated sigma to avoid the over smoothing. You can try the different values in your case, and then decomposition level is 5, and then wavelet is a coeflet 5, multi-channel is true, and then convert to YCBCR is also true. The rescaling is true, and these are commands for calculating the PSNR as I described in the previous case, and then these are the plotting commands. So here I am plotting the original image, that is IMG, and here I am plotting the noisy image, that is IMGN, and here I am plotting the denoised output that we are getting from the base method, and here I am plotting the output image, denoised image, which I am getting from the VisuShrink method, and here I am printing all those PSNR values. So PSNR between original and noisy image, PSNR in between original and denoise using VisuShrink, and the PSNR between original image and the denoise using base method. So let me execute this program in Python. So let me jump to my Spyder IDE. This is my Spyder. So this program is already written here. So let me execute this run button to run this program. Okay, so this is what output I'm getting here. So let me zoom it to see the output. So this is my original color image, and this is the noisy image. You can see the noise, and this is denoise output using base, and this is denoise image which I'm getting using the VisuShrink method. So let me see the PSNR values. The PSNR between original image and the noisy image is just 17 dB, and the PSNR between original and the denoise using VisuShrink is 25. So obviously there is improvement from 70 to 25. And then PSNR between original and the denoise using base method, that is 26.67. So there is a further improvement of more than 1 dB as compared to the VisuShrink in base method. So obviously the base is giving the better result. So let me jump to my presentation. So these are the two programs which I have explained you for grayscale images and color images. So that's it for this video. Thank you.